In this video on stellar radiation, we're going to see how one measurement can enable astronomers to determine other quantities. And this is really important in astronomy because our observation of the stars is generally from the Earth rather than from the star itself. And specifically, we're going to look at how the radiation emitted from a star enables us to work out its temperature, its power output, and from those things, its radius. And in future lessons, we'll develop this further to look at where the star is in its life cycle and its chemical composition. We're going to look at two laws in this video, Stefan's law and Wein's displacement law. So firstly, Stefan's law. You will recall that we've come across the terms power and intensity historically. Power is the actual output of an object. So in this case, the star, it's the number of joules per second being emitted by the star. But we observe the intensity of the star because we're some distance r away, and that power varies according to the inverse square law. And the power is shared out over the surface area of a sphere, and the surface area of a sphere is 4 pi r squared. So astronomers are measuring the intensity of lots of different stars, and they are observing there is a relationship between intensity and temperature. Intensity is proportional to T to the power of 4. And so we can convert that into a formula by introducing a constant of proportionality. Intensity is sigma T to the 4. Sigma is the Stefan-Boltzmann constant with a value of 5.67 times 10 to the minus 8. In terms of units, the units of sigma come from the units of intensity divided by T to the 4. Intensity, if you recall, is watts per meter squared. And you'll notice with temperature that we're going to use the absolute temperature scale and measure that in Kelvin. So T to the 4 has units Kelvin to the 4. And so the units of the Stefan-Boltzmann constant are watts per meter squared Kelvin to the minus 4. Now, where we've had similar relationships historically, we've used the constant ratio test. And in this instance, the ratio of intensity to T to the 4 is constant. So I1 over T1 to the 4 is equal to I2 over T2 to the 4, and so on. And we'll look at the usefulness of that shortly. Now, we can relate intensity back to power. Intensity is power divided by area, and therefore power is intensity multiplied by area. And astronomers refer to the power output of the star as its luminosity. So luminosity is the actual power of the star, and that is equal to I multiplied by A. So A is the surface area of the sphere, 4 pi r squared, and intensity is sigma T to the 4. And so that is the formula for Stefan's law. Now, it's really important that we define carefully what we mean by R and T. We are going to define R not as the distance away from the star, but the radius of that star. And therefore, T is the surface temperature. Okay, because if you are at the radius of the star, away from the center, you are on the surface of that star. Okay, so it's really important that we don't get muddled up, particularly with what R is and isn't. Okay, R is the radius of the star and T is the surface temperature. And so if we go back to the constant ratio test, we can look at how useful that is. So let's imagine that we've got two stars, star A, and it's got a surface temperature of 3000 degrees C, and it's got a luminosity L. Star B has a surface temperature of 2500 degrees C, and we would like to know what its luminosity is in relation to the luminosity of star A. We're going to assume both of these stars are the same size, and you'll see why I made that statement a little bit later. Right, first things first, we have to convert into Kelvin by adding 273 degrees. So that's what those two temperatures become. So the intensity of A over the temperature of A raised to the power of 4 is equal to, forgive me, let me just go back. I meant to say the luminosity of A is equal to the luminosity of B divided by the temperature of star B raised to the power of 4. And it's the luminosity of B that we would like expressed in terms of the luminosity of A. So if I rearranged that accordingly, we get that. Substitute in the data. The temperature of B was 2773. Raise it to the power of 4, and the temperature of A is 3273. And a really obvious comment now, failing to raise these temperatures to the power of 4 is going to have an enormous impact, isn't it, on your final calculated answer. So therefore, the luminosity of B, if we solve that, is 0.52 times the luminosity of A. So what's the significance of that? Luminosity of B is about half that of A. And yet there wasn't a significant temperature difference between them. Okay, and that's the impact, isn't it, of raising that temperature to the power of 4. So that's Stefan's law, relating the luminosity to the radius and the surface temperature of that star. However, when astronomers began to look at how that power was being distributed by a star, they noticed that there wasn't an equal amount of power from every wavelength being emitted. And so what they did in response to that is they began to model what that might look like mathematically. So, as we'll see later in the unit, stars are emitting radiation. And we've seen this idea before in quantum physics, whereby an excited electron drops down to its ground state and releases some of that energy, or releases all of that energy in the form of a photon. When we're considering stars, they're reasonably dense, and obviously they're incredibly hot, and they produce what are known as continuous emission spectra. In other words, we've got photons of all wavelengths being emitted from the star, from red all the way to violet. And so around about the 1900s, scientists began modelling this mathematically, and to do that, they invented an idealised surface, which they called a black body. Now, the property of a black body is that it absorbs perfectly any radiation that's incident upon it. It doesn't matter what the angle of incidence is, and it doesn't matter what the wavelength or the frequency of that radiation is. In other words, it's a perfect absorber. And therefore, it's a perfect emitter. It will emit the maximum amount of radiation possible for a given temperature of object. Now, in reality, few objects are perfect black body radiators. However, it does turn out to be a useful approximation for us when we're considering stars. And specifically, any deviation from this perfect black body radiator tells us something about the physical and the chemical composition and properties of those objects. And astronomers and we will use those later in this unit. The key thing, though, is that the distribution of wavelengths depends very much on the temperature of the object. And to show you that, let's look at this PhET animation. You are looking at a plot of intensity against wavelength. Okay, so the y-axis is labelled spectral power density, but in terms of the units, it's megawatts per metre squared. And we're plotting that against wavelength. Across the top, you'll notice that we've got which part of the electromagnetic spectrum each wavelength region corresponds to. And just to help us, the visible bit has been color-coded according to those colors. You are looking at the output from a traditional filament lamp, a filament light bulb. So this would be a piece of filament reaching a temperature of about 2900 Kelvin. And you'll notice that you've got this continuous distribution of wavelengths, but you can clearly see that the power output is not the same across each wavelength. It looks quite similar, doesn't it, to the Maxwell-Boltzmann distribution that we saw in the ideal gas unit, although it isn't that. But we have got an asymmetric profile. And it's where the peak is that's quite important. The peak wavelength is somewhere in the infrared region. And that means that we get the greatest power output from our light bulb in the infrared, i.e. the thermal region. And you know, traditionally, light bulbs get incredibly hot. They're incredibly inefficient. About 80 to 90% of the power output of a light bulb is, in fact, thermal energy. In terms of where it is in the visible spectrum, the most dominant power output is kind of red into kind of the orange into yellow part of the spectrum. There's very little green, blue and violet. And that corresponds with the colour of a typical light bulb. It is orangey yellow in colour. So that is the profile then of an object that's emitting radiation according to that continuous spectrum. Now let's change the profile and we'll just take a snapshot of that and let's look at what happens when we now have a much hotter object. So let's look at our sun with a surface temperature of about 5,700 Kelvin. Now we need to zoom out a little bit to see what's going on here. And you'll notice that the peak wavelength produced by our sun is in a different place to what it was for the light bulb. It's actually at a lower wavelength. It's shifted left. It's now in the visible part of the spectrum. It's somewhere around the green region. And so what that's telling us then is that our sun is producing some infrared, but the most dominant power output comes from the visible region. And breaking that even further, the peak wavelength is somewhere in the green region, but also we get some ultraviolet light being produced from our sun as well, and that fits with what we know about our sun. Take a snapshot of that, and now let's look at an even hotter object. So let's look at a star that's 8,450 Kelvin, and you'll notice now that the peak of that wave, and if I just zoom out and then zoom back in again, the peak of that wave has shifted even further left to shorter wavelengths. The peak is now ultraviolet. And so we're seeing a pattern, aren't we, between temperature and peak wavelength. As I increase the temperature of the object, the peak wavelength moves to shorter and shorter wavelengths. There's an inverse relationship between peak wavelength and temperature. And that's what we're going to look at now in the second of our two laws, Wein's displacement law. And you'll see in front of you that characteristic peak that we had a look at a moment ago. So when scientists were observing stars, they noticed that the peak wavelength was proportional to 1 over temperature. And the way that that was described at the time was that as you changed the temperature, you displaced the peak. You displaced the position of the peak, and hence the phrase displacement law. So if that relationship is true, lambda peak multiplied by temperature must equal a constant. And so again, that kind of constant ratio idea that lambda peak for object 1 and lambda peak for object 2 are equal to each other. And again, that's a really useful relationship that we're going to use often. Now, you don't need to know what the constant is. You're not given that in your data and formula sheet, but it has a value of 2.90 times 10 to the minus 3, and those units are meter Kelvin, not millikelvin. Okay, meters from the units for wavelength, and Kelvin obviously from the units of temperature. So it's possible then to work out the peak wavelength produced by any object above absolute zero. So let's work that out then for you and I. Okay, so for a person. So the peak wavelength being emitted by the average person is equal to that constant, 2.9 times 10 to the minus 3, divided by temperature. Average temperature of the surface of a person is a little under 37 degrees. So we'll go with about 32 degrees. And when we calculate that, we get a peak wavelength of 9.5 times 10 to the minus 6 meters. What is that equivalent to? 9,500 nanometers. Now, we know that the visible light, roughly the center of the visible light spectrum is about 500. So it's a significantly longer wavelength than visible light. It falls within the infrared part of the spectrum. That makes sense because you and I are emitting thermal energy all of the time. And so the peak wavelength that you and I are emitting is thermal energy. If we looked at the distribution, we would see that our distribution falls outside of the visible light spectrum. And obviously, you and I are not producing any visible light. It's thermal energy that we're producing. Okay, you could do a similar calculation and compare this to the sun. And remember, we noted that that was in the green region. So let's just check that that's consistent when we do this calculation. So the surface of the sun is about 5,700 Kelvin. Add the 273 to it, and that comes to 4.9 times 10 to the minus 7 meters, which is about 490 nanometers. Okay, and that is consistent with photons of green light. Okay, so that's how we do a calculation with Wein's law. Let's just have a look at the kind of the ratio idea. So let's imagine we've got two stars, star A and star B. Star A has a temperature of 750 degrees C, and star B has a temperature of 960 degrees C. First things first then, we've got to convert those into kelvins by adding 273 to each. So lambda A TA is equal to lambda B TB. And so now I can express the wavelength of lambda B in terms of lambda A. Sorry, that should be TB. Okay. So lambda B is equal to 1023 is TA, 1233 is TB, lots of lambda A. Lambda B, if you solve that, is 0.83 lambda B. Okay, so the peak wavelength, and again, let's be clear on what we mean by lambda in this case. It's the peak wavelength emitted by star B is 0.83 times the wavelength of light emitted by star A. Just to change that. Okay, so therefore, when we're looking at different stars, we get the same characteristic profile. Okay, that distribution of wavelengths, but as the star is hotter, the peak is shifted to lower wavelengths. So let's look at Stefan's and Wein's law and how they apply to this profile. So Stefan's law relates luminosity to the area under each curve. And the blue star, being the hottest star, has the greater area under the curve. And so the greater luminosity, the greater power output. Wein's law relates peak wavelength to the inverse of temperature, they're inversely proportional, and you can see that as the star gets hotter and hotter, the peak wavelength moves to lower and lower wavelengths. Just a non-astronomy kind of example then, we can express colour in terms of wavelength and temperature. And this is something that manufacturers often do, so not something that probably interests you greatly, but when you buy a light bulb from a shop, often the colour of the light is expressed in Kelvin. So if you want a nice warm colour, you want something like a 2700 Kelvin light bulb. So if you apply Wein's law to that piece of data, you can work out the peak wavelength, which corresponds to a nice warm colour. Okay, so we can express colour in terms of Kelvin, in terms of temperature. I mentioned earlier that any deviation from that kind of perfect black body distribution tells us something about composition. So here is an example of the profile from our sun as measured at the top of our atmosphere and the surface of the Earth. So if we have a look at the surface of the Earth profile, you notice that there's bits missing. There's quite a bit of deviation, isn't there, from that kind of perfect black body distribution. That's telling you something about the atmosphere. So some of those missing pieces of energy have been absorbed by the atmosphere, and we could relate this to resonance. So each molecule has a resonant frequency. It has a wavelength of light that it is able to absorb. And so therefore we can deduce chemical composition by looking at that deviation from that perfect distribution of the black body radiator. Okay, final thing. Once we know temperature and we know power output, we can determine radius. And this is a really powerful thing to be able to do. So we've got two objects. We've got the sun and we have some kind of star. We are told that the peak wavelength of the sun is 500 nanometers. And we're told that the surface temperature is 5,800 Kelvin. Now, at this point, you might reasonably think, well, I could have worked out the surface temperature from the peak wavelength using Wein's law. But that requires you to know the constant, that 2.9 times 10 to the minus 3. And that isn't something that you're expected to know. So examiners have provided us with the surface temperature. And we've got a luminosity of 3.85 times 10 to the 26 watts. We have a nearby star, and it's got a peak wavelength, and it is shorter than that of the sun. So we're going to deduce it must be hotter than the sun, and it's got a luminosity that is 10 times the luminosity of the sun. We are able to work out its radius. Okay, the first thing then that we need to know if we're going to work out the radius of the star is what equation is going to get us there, and it's going to be Stefan's law, isn't it? 4 pi r squared sigma t to the 4. I kind of know what the luminosity is. It's 10 times the luminosity of the sun, and I know what the luminosity of the sun is. Radius is what I've got to find. I don't know its surface temperature. And so I'm going to use Wein's law to work that out. So the peak wavelength of the sun multiplied by the temperature of the sun is equal to the peak wavelength of the star multiplied by the surface temperature of the star. And I now can rearrange that to find the temperature of the star. So that is the peak wavelength of the sun, 500 nanometers, multiplied by the temperature of the sun. It's in Kelvin, so I don't need to convert that. And I'm going to divide that by the peak wavelength of the star. And you'll notice I didn't convert either number from nanometers into meters. I don't need to. That would cancel out if I converted and expressed both of those times 10 to the minus 9 meters. Solve that, and we get that the surface temperature of the star to be 9355 Kelvin. Okay, so now I know everything I need to in order to use Stefan's law. Radius is what I need. So if I rearrange that, it's luminosity over 4 pi sigma t to the 4, and I need to square root that. The luminosity of the star is 10 times that of the sun. Divide that by 4 pi, multiplied by Stefan's constant. An interesting set of numbers, 5, 6, 7, and 8. Multiplied that by T to the 4, and it's the temperature we've just worked out, isn't it? 9355. Now, I would strongly urge you to keep the exact temperature in your calculator because you're about to raise it to the power of 4. So rounding errors are going to be really significant in this case. And that gives you a radius of, when you round it exactly, 840 megameters, 840 times 10 to the 6 meters. So to conclude, we have been able to determine the temperature and the power output of a star and the radius of a star based on the radiation that it emits. We've got Stefan's law, which relates luminosity, radius of star, and temperature of star together. And we've got Wein's displacement law, which relates the temperature of the star to the peak wavelength that's emitted.